can't tell. Are we recording?
Yeah, I just turned it on.
Oh, there it is. Okay, sorry. All right. Hi, welcome for people watching the recording. This is the first session of the Quantum Computing Book Club series. We're going to talk briefly about chapter 1, and then really in the future sessions, there's going to be much more technical content for us to talk about. So this book has an interesting structure, talking about that before we get into the details of chapter 1. So chapter 1 is just like motivation intro about, why quantum computing. And then there is a section on foundations. So chapter 2 talks about computing, and really when we say classical computing in contrast to quantum computing, what the heck do we mean by classical computing? And then all the math that's used in this book is covered in chapters 3 through 6. So technically speaking, you don't need to know any math. It's not assuming you know it because it's all covered, but it's going to go very quickly. So for those people who have linear algebra and beyond, I think we're going to probably be pretty comfortable with chapters 3 through 6. Chapter 5 is kind of long. I think it's like 75 pages or something like that. So I tentatively allowed for 2 weeks if we want, but depending on, this is for you guys. So depending on how it goes, if you want, I think we could probably cover it all in 1 week, potentially. But so the schedule is just, Saturdays look something like this. And so either September 24th or October 1st, depending on if we reduce things, we'll get to part 2 of the book. So then it's no more about foundations, but it's really just starting to go through what is a state space, and therefore what is a qubit, and then how does sort of quantum circuits work? How do you do the math? How does all this work? What happens when you try to observe the result? All that stuff about quantum computing, and ultimately it leads us up to some of these interesting things about algorithms and the idea: can we do certain things faster with quantum algorithms than we can do with classic algorithms that we're familiar with? So that's just the general structure in terms of like what this book is and whatever. And again, for the people who are strong with math, these next few chapters, I think you'll find the math content pretty straightforward, but the author does do a good job of sort of laying the groundwork for questions or for things that are going to be different than what we're used to seeing up ahead. So I had kind of debated, do we just say, hey, this book club's for people who know math and jump straight into part 2, chapter 7? But I think the author does do a good job of introducing certain things. And so Ryan and I had talked about possibly starting in September. And so I thought, okay, why don't we just start sooner, start in August. And then I think for many of the people here who in the polls said that, they're familiar with linear algebra and beyond, we'll probably be able to get through the math stuff pretty quickly. Any comments or questions just in terms of the weekly structure of the book club, that kind of stuff? Okay, so then let's talk about chapter 1 as sort of an example for what the rest of the book club series is designed to look like. So basically what I've done here is I've created an outline for chapter 1. And you can see here I have the sections, and where the author has questions, I've sort of dropped the questions into the outline. When we get to the more technical stuff, these questions are, going to be more technical, right? Since this chapter is just sort of motivation, I'm not necessarily expecting that people will have questions about these, but I just wanted to demonstrate. So the plan right now, what I'm thinking is that I'll be preparing this outline for each of the chapters, and it's going to be something sort of like, okay, so in this week's chapter, the author started talking in section 1.1 about the mysterious quantum bit, and he gave this analogy of a classical light switch versus a Q light switch. Did anybody have any questions about it? Any comments? Is there something that we want to discuss? Either, whatever, kind of along those lines. So as Ryan said, it's not going to be about us trying to do a lecture to cover the content. that's in there. So this is why, really, I think this book club will be directed towards people who, want to read the book. Now, I know that life intervenes and stuff like that, and so there very well will be weeks where you fall behind, you're not ready, and of course, everyone's still welcome to attend. This isn't meant to be pressure. I just think that the material will be complex enough that it'll be too difficult to just try and absorb it from lecture. People will really need to read the book, and some parts may be easy and other parts it's just going to be like a head scratcher. I was looking at something very simple the other day, this 2-qubit controlled C-NOT gate, and I was having trouble with some of the math, and I realized that I just had a fundamental misunderstanding about, I thought something would look like 1010, and it was actually just 1000. And so until I worked through that had this misconception, just nothing was adding up. And so I just, so basically I chatted with Ryan. It's like, we're not even going to try. We're not going to try to explain this material and go through it at that speed, but rather let people work through. You can use the Slack during the week. If you want to ask something, you're like, hey, I don't want to wait till Saturday. Let's see if somebody can help me with this. That's totally fine. But then otherwise on Saturday, really, it's going to be talking about this. And then if we are fortunate enough where people don't have too many questions and people have gotten through it, at certain points, we may just look at some sample problems, or people may have things that they want to talk about. This book is really focused on the computing side of it. So it's not really going to get much into how do we actually build quantum computers. Okay. So I'm not expecting much discussion about, about trapped ions or topological qubits or things like that. But if we have time, and for those of you who actually are really interested in this stuff and read more about it, then if there's, news and other stuff, how that applies to what we're talking about, I think that will be fair game. That will be fun as well. All right. So any comments or questions on that part? All right. So having said all that, I'm going to somewhat depart from what I said, since this is chapter 1. It's like, I don't know if people have actually read the chapter. I am going to actually talk about it in a little bit more detail, but my plan is not necessarily to do that in the future weeks. Okay. So in section 1.1, and again, all of this stuff is just motivation. The details for all of this are going to be repeated when we get to the technical content. But he does do this motivation where he says, you can imagine a classical light switch where the light is either on or a light is off. And he said, what's interesting is when the light switch is not in the same room as the light. So if you flip the switch up and you go to the other room, you can check and you can see the lights on. You flip it down, you go to the room, you check it, you see the lights off. But with a quantum light switch that he's having us imagine, this little sphere, he says you can touch it anywhere on the sphere, and if you touch it at the tip, at one end it's on, and at the other end they're off, and in between there's some probability that it's on and it's off. But the really interesting thing about this, which I think people who are curious about quantum computing are already sort of familiar with this concept, so it's not really like a spoiler, but it's not the case that there's a hidden state. It's not the case that if I put my finger on the equator of this sphere, that there's a 50-50 chance that the light will be on or off, and it's on right now. I just don't know it. No, in fact, the really interesting thing is that the state is indeterminate until we go and observe the result. And so that's what makes this quantum business very different from other things that we're doing, because we do have probability distributions that we deal with a lot in machine learning, but the probability distributions, act in terms of this physical state, as opposed to this idea that it does not actually have a value until observed. Okay, so then section 1.2, starting to get into the motivation. gives an example of caffeine. Okay, so here's the formula for caffeine, and he says it would take about 10 to the 48th power bits to represent the states of all the atoms and electrons in a molecule of caffeine. All right, but theoretically, about 160 qubits could hold that much information. So not saying exactly how we would actually encode all that information or manipulate it, but the author says it gives us hope. So, you know, I think an example would be, let's say, like I've read a bunch of papers talking about how are we going to train a reinforcement learning agent to play poker. And one of the problems with poker is that there's many, many, many different possibilities for what cards your opponents could hold and what cards could be in the center. And it just becomes this somewhat exponential explosion of possibilities. So, for example, in poker, you say, okay, well, let's say there's like 52 cards. And so if the other opponent has 2 cards, then 52 times 51, something like that, you know, approximately, you know, 2,500, 2,000 different hands they could be holding. And then when they bet, even if you assume you have perfect knowledge of their strategy, that changes the probabilities of what you think that they're holding. Okay. And then you know, there's another card and then things happen. And so, you know, ultimately we can keep track of these distributions, but we have to sort of multiply them all together. All right. So if I had like a 20-sided die, but it was not a fair 20-sided die. In other words, the probability of all the 20 different outcomes were different. Okay. I could keep track of that, and I could have a table in a classic computer with 20 different probabilities. And if I had a second one that was also an unfair, I could keep track of that. And if I wanted to know the possibility of all the combinations of those 2 dice, basically, if I were going to store them on my classical computer, right, then I would need 20 times 20. I would need 400 memory slots to do the probabilities for each one of these combinations of things. But in nature, you don't need it. You can just roll the dice, and the probabilities will be observed. The probabilities will naturally happen. All right, and so that's essentially what we're going to look at with these qubits. Is ultimately you're able to using this thing called superposition, you're able to encode multiple values simultaneously, and therefore, if you can design the right algorithms, you can have those interact, and you don't necessarily need either the memory or the explicit computation for all of those. All right, next section, why quantum computing is different. I think I talked about it. I actually didn't understand the author's analogy about this quantum H function here. I don't know if any of you guys read the chapter, and if you can help me. I don't think it's that important. I feel like I understand it, but the gist of this, but I didn't actually really understand his coin flipping thing. So I don't know. Did anybody read this section, and did this R and H business make sense? Any more sense to you than it did to me? All right, I'm going to keep going.
I didn't get it either.
Yeah.
Yeah,
but
it
so
didn't make sense to me either.
Okay, I'm glad to hear that. So the main thing here is he says, right, so a classical byte with 8 bits can represent 256 different values one at a time. What I was trying to say in my thing about like rolling dice or poker is that if you have 8 qubits, you can represent all 256 values as some type of probabilities or whatever simultaneously. And so then you can operate on these, you can interact them with other things, and so that's where potentially you're computing what we consider to be a vast number of calculations, potentially an exponential number of calculations, but the number of steps in this quantum computer is less. It's not necessarily exponential. So actually the examples that he gives in the next couple sections, you guys actually hit the ball when you guys were introducing yourselves. So that's actually nice. gives an example for artificial intelligence of, if you guys are familiar with support vector machines and the kernel trick, basically we can transform our actual raw inputs into a different space, potentially a higher dimensional space, potentially an infinite dimensional space. But the kernel trick is that we do not actually literally perform the transform, calculate a support vector machine in that transform space, and then transform the results back. We have a shortcut because we, for certain transforms, not everything, but for certain transforms, we can calculate the dot product in the transform space without having to actually do the transform. So this kernel trick is like a shortcut, so to speak, where the number of mathematical operations you're performing is actually less than theoretically what you're doing, because theoretically, if you transform it to a 500 dimensional space, maybe you should be operating on whatever the algorithm is. I don't remember, n squared, whatever, on 500, but you actually don't have to because you're using this kernel trick. And so he's making this analogy that in the quantum world, there may be things that it would take us a lot of explicit calculations on a classical computer, but this kind of gives us a shortcut. For financial services, he talks about Monte Carlo methods. And so sometimes if it's too hard to empirically calculate a distribution, what you can do is you can sample. So we see a lot of this in machine learning, right? We have bagging and bootstrapping, and we also use Monte Carlo methods and things. You see Monte Carlo tree search in reinforcement learning. And so it may be the case that a quantum computer may not give us the like direct, I don't know how to say this, I'm not saying this well, but in some cases you have a closed form equation and you just solve it and it says the answer is whatever. So some of these quantum algorithms may not be about closed form quantum algorithms that just give you a number, but rather algorithms where you are doing sampling and that tells you about the distribution. But in the case, if the algorithm requires square root as many samples, or even better, log as many samples, then of course you're going to be able to have as accurate of a simulation of the distribution, but with far fewer steps, far less computing. And then cryptography. So we know that there's Shor's algorithm for factorizing integers into primes, and RSA, public key encryption, fundamentally depends on this. But the author says, hey, people don't need to freak out overnight because these are actually very large numbers, and you're going to need a pretty large quantum computer before you're able to do this. So you should definitely plan for stronger algorithms that there is no known way to defeat them with a quantum computer. But he said, it's a little bit hyped up. Another thing he talked about that I don't know anything about, but we can talk about a classic qubit, which is a you have some quantum mechanical object, and let's just talk about like a two-state system, but we're talking about a closed, completely independent system, and it's really hard for people to build such a thing, such that there's actually no interactions. So he threw out this factor of 1,000. That seems a little bit high to me, but I don't know. I don't know this stuff. That basically, if you want to have error correction, that you might need 1,000 qubits in order to have a fully error corrected single qubit. And that seems to me like there's going to be some ratio there, but 1,000 seems like pretty heavy loss. And then of course, if somebody comes up with some really awesome computer, that some topological qubit or something that doesn't, then of course that ratio drops all the way down to 1-to-1, and then we're a little bit closer. I mean, we still don't have more than maybe double-digit number of qubits, and you're going to need thousands, but we're a lot closer if you don't need to dramatically multiply the number of qubits to deal with error correction. All right, so then in summary, this first chapter says there's some interesting applications And basically, using superposition and entanglement, we can encode multiple values into a set of qubits instead of only a single value. And so there's potential applications like chemistry, financial services. We're not there yet. I think it's also interesting that on the theoretical side, as far as I know, there's very few. There have been quantum algorithms that are fast that people have developed, but very few of them people have proved that there isn't a classical equivalent that's as fast. So in other words, there's classical algorithms, there's some quantum algorithms that are faster, but the ones of those that have been proved that you can't develop one versus we just simply haven't figured out one yet. There's actually not that many. And I believe there's actually a few cases where somebody had an algorithm that they said, this is a quantum algorithm and we think that this is faster than any possible classical algorithm. And then people have said, oh, well, now that we see that algorithm, they've actually devised new classical algorithms that have sort of the same running time as those quantum algorithms. So it's kind of interesting that there's all this promise and hype around quantum computing, but from a theoretical perspective, I think there's very few algorithms that have been proved to be faster than any possible classic algorithm. All right, so that's, again, the plan in future weeks is not to really go through this like a lecture, but rather to just sort of say, here are the topics, and to see if nobody has any questions, if everybody's comfortable, then we won't necessarily talk about those sections. And then we can stop for the different questions, because again, when we get to the meat of it, these questions will actually be like math problems. They will have answers. The answer will be 17, or the answer will be a vector, or the answer will be how do you prove that such and such is true, or something like that. So there's going to be much more meat to those, and that's why I'm planning to highlight those so that we can pause if people have difficulty with any of those. Okay, so that's a quick overview of chapter 1, and again, a little bit of highlight of just sort of our thinking, the approach for this book club. So any comments, any questions, suggestions, thoughts about other things we could do to
I know randomize, sorry?
Yeah, sorry, go ahead. Yep.
I know randomized methods, and as far as I know, quantum computing means applying randomized methods. Randomized methods works because they do not measure actual time for each run. They measure estimated value, average. And if you, in particular, if you know your area, you can pick up your random numbers with a particular distribution, so it could be more or less more often cases which appear with more frequency. But the thing is that you can run into a very bad case. The same is with classical computing. It is just with classical computing, funny enough, it happens more often because they go systematically through all cases, which means that if they stuck in a bad spot, they will be stuck in it pretty much, well, for a long time. And quantum computer allows to jump off to another place, which could be easier. So it is not like quantum computing has some kind of specific way to find a better case. It is just because it jumps here and there, picking up different parameters and checking them. And it is more efficient than systematic listing of all parameters and going through them.
Yeah, it's definitely more efficient to not go through things sequentially. It occurs to me that if you somehow formulate things as a quantum problem and you get them formulated exactly so that in the end you, let's say, have a qubit, and the problem you're trying to solve, right? The qubit, the probability that it's a 1 is exactly matching the number that you're trying to calculate between 0 and 1, right? The nice thing about that is if you do this experiment multiple times and you measure it, I don't think you need to worry about like confounding factors or whatever. Like your measurement will be exactly statistically random. It's guaranteed to be random, you know, if you formulated it right. And so if you measure it 1,000 times and then you get, you know, 768, well, then that's saying the answer is 76.8% is the value you're looking for. And then of course you have your I don't know, whatever your confidence interval. So ultimately you have to, depending on the precision that you want, you have to repeat the experiment that many times in order to get more digits to say it's, well, it's actually 78.1, you know, 78.12, 78.123, whatever, depending on the number of repetitions you do.
I think for me, one of the interesting pieces of this equation is I think the algorithms and the possibilities are very interesting, but I think one of the things that I might take an interest in on the side is just what is the actual kind of growth of our ability to make quantum computers in terms of are we following Moore's law? Are we going faster than that? At what point do we think quantum computers will truly be viable and be solving actual problems? At current rate, will we end up anywhere useful in the near future, or do we need some major breakthrough to even get to that point?
Yeah, it's interesting. I think we're going to need, well, I don't know, some advances. I don't know if they're breakthroughs.
Yeah, if you need 1,000 bits to get something that isn't too noisy, and you've only got double-digit bits right now, it's, I mean, how are these things even producing anything that isn't just random noise?
Mm-hmm.
Yeah, and there are like quantum computer simulators where you can like simulate really small problems, and it's, of course, because it's simulation, it's not actually any faster, but at least, you know, learning. So I think that if, as somebody who's, you know, very interested in how we solve problems, and that brings me to my interest in machine learning, right? Assuming there is an advance or a breakthrough with quantum computing, then I think it'll be nice to understand how it works and understand these things. And then if I'm interested, I can say, oh, okay, I can help, you know, program and devise algorithms for this brand new quantum computer that we have, instead of waiting till it happens and then finding out about it. Anybody else? Any other comments, questions, thoughts, suggestions? All right. So for next week, we're going to read chapter 2. So this is the chapter on classical computing. I think everybody said they know at least one programming language. So I think this is going to be pretty light material. But again, the author does sprinkle in setting up some questions that will get more interesting when we get to the actual quantum stuff. And so again, my thought is that the first few weeks, for many of us, hopefully we'll be able to go through this pretty quickly. And when we get to the actual part 2, get to 1 qubit, 2 qubits, quantum circuits, quantum algorithms, that's when all of a sudden the learning curve is going to get much steeper, because all of a sudden it's just like, okay, and so, you know, here's a whole bunch of, you know, matrices and you know, whatchamacallit, tensor products of vectors, and we're going to talk about these unitary matrices and conjugate transposes and blah 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 blah, and boom 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 boom. It's all gonna come really fast. So if the first few weeks seemed light, just enjoy it, because it's gonna it's going to pick up really fast. All right, Ryan, maybe we can end the recording here.